Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hazim Shahmi bin Muhammad Yusof. My matrix number is DE210091. Okay, so today we will present our group assignment for BEV30503, which is control system subject. Okay, our group consists of 5 members, which is the first member is Syarul Ali bin Zifka Husni. The second member is me, Muhammad Hazim Shahmi bin Muhammad Yusof. The third member is Anis Fahana binti Raimidin. The fourth member is Khairunisa binti Yusri. And the last member is Pravin Raj, anak lelaki kanan. Okay, we are from group 11, section 2. Okay, so I will start with the introduction. Okay, a mathematical model is a representation of a physical system in mathematics that is created using the system proper governing laws. Okay, what is a motor? A motor is an electromechanical component that produces a mechanical output from an electrical input, known as a displacement output for a voltage input. Okay, next is what a DC motor. A DC motor, which also known as a direct current motor, is a type of electrical device that uses direct current to generate a magnetic field that converts electrical energy into mechanical energy. Okay, so next we must know about the PID controller. A PID controller is a device that regulates temperature, flow, pressure, speed, and other process variables in industrial control application. The most precise and reliable controllers are PID, which means proportional integral derivative controllers, which use a control loop feedback mechanism to control process variables. PID controller is a well-known method of driving a system towards a desired level or position. Okay, the same method for solving direct current circuits are used in the analysis method, known as sinusoidal steady-state analysis or SSSA, to analyze AC circuit. That's all.
Assalamualaikum and hi, my name is Anis Fahlan. Telling me that my memory number is DE210039. So today I want to present about the literature review. Okay, first we go to the PID controller. PID controller actually consists of three types, which is a proportional P, derivative D, I is integral. So each of them has certain parameter that must be set to be able to operate properly. And most of the control system that are implemented with the use of PID controller because of the simple structure. And then to design a PID controller, usually we use a method of try and error. When this PID controller device parameter are selected incorrectly, the device output is inaccurate and its result is unreliable. So next we go to the P controller. P controller is a proportional control that controller action is described as a proportional when the output signal is proportionate to the difference between the measure value and desired value, and also it has a type of feedback control. And next, the P controller is mostly used in first order process with a single energy storage to stabilize the unable process, and also P control is used to decrease the steady state error of the system. Okay, next we go to the PID controller. PID controller is we call a proportional and integral controller, and the common technique is in the control system we need to adjust for difference in between the required set point and actual value based on the feedback. And also a PI controller is a type of feedback control. So when we adding the proportionate action result in a quicker response time than I control. In addition, PI controller are most frequently used in an industrial application because of the easy to construct and easy to design and also inexpensive price. Okay, next we go to the Ziegler-Nichols method. Okay, Ziegler-Nichols method is also we use for the method of turning P, PI, and PID controller. Okay, this method is start by zeroing the integral and differential gain and raising the proportional gain until the system is unstable. Okay, the Ziegler-Nichols method is used to determine value of turning parameters such as proportional gain, which is Kp, integral time, Ti derivative time with Td, that based on the transient response. Okay, this method can be used for the open loop and closed loop. Okay, next we go to the Siemens mixer control system. Okay, the Siemens mixer is also we call the concrete mixer. Siemens mixer are always used in building material that the control system of the concrete mixing station play an important role in the technique and economic indicator of concrete production. Okay, therefore, the advanced control system of the concrete mixing station is of great significance for concrete production. Concrete mixing may be not to be precise operation but this is depending on the application. Concrete mixer are tools that can efficiently and accurately prepare concrete mixer of various strengths. Some concrete mixer can even pour the concrete mix just where the construction is being done.
Doctor, my name is Pravin Raj, son of Kandan, and my metric number ID is CE210 and 202, and also I'm from group 4 as well. So this is our problem for group assignment. So this is our question. So my part in this question is literature review and also part G. So first I want to explain the literature review that I made. So this is the first literature review. The title is the cable fault diagnosis for XLPE cable based on 1DC NNS build STM network. This is which was published in the Journal of Control Science and Engineering, gives an overview of the history and development of PID controllers, which is include the types of PID controller and how they are designed and tuned. The PID is designed for keep the electricity supply stable when a short circuit fault happens, and it's also very important to correctly identify the type of fault. A hybrid classification model is proposed for the classification, short circuits and faults. The model combines one-dimensional convolution neutral, that is 1DCNN, and the bidirectional long short-term memory network, that is BILSTM, which I said in the topic. So the circuit, two-phase grounding short circuit, two-phase short circuit, and also three-phase grounding short circuit, and the signal is fed into the network with IDCNN. So this is about the first theory or first research. The second literature is PID to active disturbance rejection control, and this is also was published in IEE translation on industrial electronics. Active disturbance rejection control ADRC can be summed up as follows. It takes the best part of modern control theory, the state observer, and combines it with the power of nonlinear feedback. And also ADRC is only possible if control is taught an experimental science rather than a mathematical one. So which means that control technology needs to be moved beyond PID, which has been standard over 8 years. In particular, there are 4 problems with PID we want to fix. They fix the 4 problems. The first is the error computation, and the second one is noise regression, and the third one is oversimplification, and the fourth one is complications. And also they do about the noise tolerant traffic differentiator, the nonlinear control laws, and the idea of method and figuring and rejecting the total disturbance with the ADRC. So the third one is closed loop geothermal system. They also use the PID in the closed loop geothermal system. And as the circulation rate goes up, the fluid temperature go down, but the thermal power go up as the work accordingly. And my next one is control system synthesis for open loop unstable process with time delay. So this project explained about how open loop system are used in transportation businesses. So we also take that as a reference for our project. And also to make 2 degrees of freedom elements or PID system that are used all the time. There are also rules for how to tune PID control in this project. And the last one is fault dynamics in robot systems. To do a certain job, these parts are not put together and packed tightly with the special controller. Most of the time, especially the robot system, and become less unuseful. Fault mistaken happen, make it hard to work. Also, according to some old news work, many kinds of fault they are studied. Also, these joints which usually connect the arm links to each other and make sure the motor, controller, and many sensors can talk to each other that are really most important part that needs to be studied in this theory. And according to the papers that we have looked at, the most important part is the hardware fault, which must be found and fixed in the real-time using methods. And also, these are the references they take from.
Assalamualaikum and hi, my name is Harnisa binti Yusri, my matrix number DE210108. So for the problem elaboration for this project, firstly, the challenge in this project is to create a PID controller that can be used to regulate and control the speed of the cement mixer. The system block diagram was constructed and developed in MATLAB Simulink to get the core knowledge required for diagram construction. Number 2, in the basic electromechanical system block diagram, PID controller is used with the input speed set to 900 RPM to 1500 RPM to assess the output shaft speed response. The mechanical system shaft speed is the output variable. Number 3, the Ziegler-Nichols technique and automatic tuning are used to manually configure proportional gain Kp, integral gain Ki, and derivative gain Kd from proportional integral, and proportional integral derivative to achieve the ideal shaft speed response in the controlled electromechanical system. Number 4, to simulate the output shaft speed response, a block diagram of an electromechanical system in an open loop control system was generated in MATLAB Simulink with the input speed variable set to 1500 RPM. And since open loop control system do not use feedback to detect whether the output response has achieved the intended input command, error signals cannot be solved. And lastly, the analysis help to minimize the maximum overshoot, rise time, settling time, peak time, and error conditions tables using mathematical calculation or MATLAB calculation to make comparison manual and automatic tuning in MATLAB Simulink to evaluate the PID controller gain.
So for the next part is problem execution, mathematical and block diagram derivation. So the parameter and value is given. So VA equal to 380 volt, JM equal to 0, JM and JL equal to 0.222 kg per meter square, VM equal to 0.003 Newton per second per radian, BL equal to 0.0005 Newton per second per rad, KB equal to 1.25 V rad per second, KA equal to 1.28 Nm per ampere, RA equal to 11.2 ohm, LA equal to 0.121 H, and N is 1500 RPM. So for the A, derive it mathematical model and block diagram. Input is VA, rated motor terminal voltage, and output is blade speed. So Laplace transform of a matrix equation, VA equal to IA times RE plus LES plus EBS. So is equation 1. So for the force equation applied to motor, PMS equal to theta MS, JM plus JL times S squared plus BM plus BL times S. So we turn JM plus JL equal to JT and BM plus BL equal to BT. So it is equation 2. So the next is Laplace transform of electromagnetic equation. EMS equal to KA times IAS, so it's equation 3. So EBS equal to KBS theta MS, so it's equation 4. So from equation 2 and 3, we get IAS equal to theta MS JT times S squared plus BT times S over KA. Next, we insert equation 4 and equation 5 into equation 1. So VAS equal to IAS times RA plus LAS plus EBS. So we get VAS equal to theta MS times JT times S squared plus BTS over KA times with RA plus LAS plus KBS theta MS. So we assume that ZA equal to JT times S squared plus BTS times RA plus LAS. Therefore, we get the VAS equal to theta MS times ZA over KA plus KBS. Next, theta MS over VAS equal to KA over ZA plus KABS. So theta MS over VAS, we get KA over JT S squared plus BTS times RA plus LAS plus KABS. And lastly, we get the theta MS over VAS, KA over S cube times JT LA plus S squared times JTRA plus BTLA plus S times KAKBS plus BTRA. So the total amount of inertia and waste expression is JT equal to 0.222 plus 0.222. We get the 0.444 kilogram per meter squared. And the value of BT is 0.003 plus 0.0005. So we get the total of 0.0035 Newton meter second per rad. So we insert the value of DC motor data into the equation. Data MS over VAS. So we get the value is 1.28 over S cube times 0.444 times 0.121 plus S squared 0.444 times 11.2 plus 0.0035 times 0.121 plus S times 1.28 times 1.25 plus 0.0035 times 11.2. So get the transfer function is theta MS over VS equal to 1.28 over 0.0537 S cube plus 4.9732 S squared plus 1.6392 S. So this is the block diagram of the transfer function. Okay, so next I will explain question B, which is determine the PID gain manually. Okay, to answer the question B, first we have to use the transfer function that we get from question A. Okay, so this is the transfer function. Okay, next we have to determine the characteristic equation for the transfer function. For that, we will use the formula of 1 plus kgs hs equal to 0. Okay, so from that equation, we will get 0.0537 s cubed plus 4.9732 s squared plus 1.6392 s plus 1.28 k equal to 0. Then we will use all the value that we get into the table for s cubed, s squared, s, and s power of 0. Okay, from this table, by using cross multiply, we have to find the value of a and b. Okay, so as you can see, the value of a that we get is 8.1521 minus 0.0687k divided by 4.9732. Okay, for B, the value that we get is 1.28k. Okay, next we have to give the equation a stable condition. How? So first we have to make an equation for A, which is A more than 0. For that, we will get k less than 118.662. Okay, second, we have to put B into equation, which is B more than 0. Then we will get k is more than 0. So we will get the stable condition, which is k more than 0, but less than 118.662. Okay, next we have to find the value of k critical. K critical is equal to k. So the value is 118.662. Then we have to use the imaginary roots below to find s squared. And we will get the value of s squared is negative 30.5412. Then we will have to find s for 1.2, which is we will get plus minus about 5.5264. Okay, next the sustained oscillation at the limiting value of k equal to k critical is 5.5264 radian per second. Okay, the period of oscillation or PCR, the formula used to find the PCR is 2 pi over omega. So we will get 1.14 second. Okay, for P, first we have to find Kp, which is the formula is 0.5 times KCR, which the KCR value is 118.662. So Kp for P, we will get 59.331. Okay, next for Pi, first we will have to find Kp, which is the formula is 0.45 times KCR. As above, the value of KCR is 118.662. So we will get the Kp for Pi is 53.3979. Okay, next for Ti, the formula is 1 over 1.2 times PCR. The value of PCR is 1.14. So we will get the Ti value is 0.95. And lastly, for Pi is we have to find the Ki. The formula used is 0.54 times K critical divided by PCR. Okay, the value of KCR and PCR is the same as above. So we will get the Ki for Pi is 56.2083. Okay, next is for PID. For PID, first we have to find the KP, which is the formula is 0.6 times KCR. Then we will get 71.1972. For TI, the formula used is 0.5 times PCR. The value for TI PID, we will get 0.57. For KI, the formula used is 1.2 times KCR divided by PCR. Then KI for the PID, we will get 124.9074. And for TD, the formula used is 0.125 times PCR, which we will get the TD for the PID is 0.1425. Okay, so lastly is for PID, we have to find the KD value. To find the value of KD, the formula is 0.075 times KCR times PCR. So we will get the value of KD, which is 10.1456. So based on the value that we get, we can put into the table 1, which is the value of KP, TI, KI, TD, and KD for the three PID type, which is P, PI, and PID. Okay, so that's all for B. Thank you.
I will present for the MATLAB part for C and D. For C, we need to create the system block diagram and manual, timing, PID controller on MATLAB Simulink and attach on the report. Okay, I will show you how to design this block diagram. Okay. First, we need to have a subsystem. When we have the subsystem, we click and then we construct the block diagram in this subsystem. Okay, I will show you. This is our subsystem block diagram. Okay, we go to the next we will go to the implement PI and PID controller using PID key from table 1. System without controller open loop employ the response each of their response versus input signal. This is our block diagram of the P controller. So this is the value of the KP and the step we fill in the value is the 1500. Okay, so we run this simulation and then we will get this graph. So next we will construct for the PI controller. Okay, so this is our PI controller block diagram. So this is the value for the KP for PI. This is value for the KI for PI. So the step we also use this 1500 RPM. So we will run this simulation and then we will get this graph. Okay, next we will go through the PID controller. Okay, this is our PID controller block diagram. So for this type, we also use this 1500 RPM, and this value is the KP for PID, KI for PID, and KD for the PID. So and then after that, we will run this simulation, and then we will get this graph.
Okay, for question E and F, so for question E, create the system block diagram for automatic fine-tuning PID controller on MATLAB Simulink. And F, develop table for comparing the PID controller gain from manual and automatic tuning. So we go to the MATLAB. So this is the block diagram for manual and automatic. So this is the manual and at the below, and this is the automatic tuning block diagram. Okay, so we put sum, and then this is the PID controller, this is subsystem, and in the subsystem we put the transfer function we get from the equation, and this is the bus creator, and lastly this is the scope we use to show the response for the automatic. Alright. Okay, for the PID controller, okay, this is the automatic gain for PID. So we cut this, we delete this. I will show the step to display a response automatic tuning. So okay, we put the new PID to this block diagram. Alright, and then alright. For this internal, for proportional integral and derivative, we put this manual calculation to the proportional integral and derivative. So for the P, KP 71.1972. And then for the integral, we put from KI PID 124.9074. And then for the derivative, we put KD PID 10.1456. And then we click apply and click the tune. So it will show you the response for manual and automatic graph. So this for the block response. For the block response, this is the manual response, and for the tune response, this is the automatic tuning response. So we can see the parameters for rise time, settling time, overshoot peak in this block. Alright, and then click the update block. So this is the automatic response, and this is the controller parameter for automatic tuning response. So P is 0.8728, I is 0.06544, and D is 2.004. And at this block, it will change automatically. Alright. To make a comparison for manual and automatic, for question F, develop table for comparing the PID controller gain from manual and automatic tuning. So from this, so we put one scope at this to make a comparison for manual and automatic. So I will run this circuit. Alright, after run the circuit, click at the scope at the right side. Okay, So after we run the circuit, so we can get the graph. Like this. So this is the input graph, manual graph, and for the purple color, this is the automatic tuning graph. Alright, so for F, for the comparison of two PID system block diagram, so this is a table, the comparison table. For the manual PID tuning, KP is 71.1972 and the automatic KP is 0.8728. For KI, manual is 124.9074 and KI for automatic is 0.6544. And then for the KD, the manual is 10.1456 and for the KD for automatic is 2.004. So that's all for question A and F. Thank you.
Which is my part G. Plot comparison to PID control response in input versus manual versus automatic tuning. Then make sure the PID control is able to minimize maximum overshoot below 10% and rise time, settling time, and peak time and error condition stable from system response without controller, then complicate table 3. So this is our MATLAB file. So first I want to run. It is done compiling. So we put 3 scopes. This is the manual scope, and this is his automatic and manual scope, and this is the manual one. So we first see the manual scope. So this is from the manual one, the waveform, and also we can see the parameters at here. For overshoot we have to click here, and we can see the overshoot settling time and peak time and all. So to see the automatic one we have to click here, and we can see the automatic waveform. And also for see the parameter we have to click the ruler symbol one here, so we can see the measurements. So we also can add measurements by double right click at here and peak finder, and that all we can edit it here, so we can find it out. And this is the manual versus automatic scope. This is the waveform of the manual and automatic, and here are the parameters for the table. And also there is another way to find the parameters that asked in table 3. So for that we have to double click the PID. We have to come down here, and at here we have to replace with the manual value the filter coefficient we just put 100, and we have to apply, and after applying we have to click tune. So we can see here the block response is the dotted line, the waveform, and the normal line is equals to the tuned response. So to see the parameters we have to click here. So we can get the parameters that is asked in table 3, the rise time, settling time, overshoot, peak, gain margin, phase margin, and closed loop stability. So that's all from me. Thank you, doctor.
As for conclusion, based on our research, the PID control system is essential and crucial to effectively controlling the speed of a DC motor. Based on the simulation results, a proportional controller KP will shorten the rise time and overshoot more, but the steady state error will not be resolved. However, an integral control KI will significantly worsen the transient response while eliminating the steady state error. Nevertheless, using a derivative control KD, the transient response will improve by increasing system stability, decreasing overshoot, but has no effect on the steady state error. PID controllers are used in almost all closed-loop industrial automation applications as well as numerous industrial process control applications. So based on our prior findings, it is clear that we were able to use control system theory, techniques, and concepts to describe and resolve the control system engineering challenge. To develop and create the DC motor system for this project, we use the MATLAB simulating software and obtain an answer for our results. So we gain a lot from this project because it enables us to increase our understanding of MATLAB through the observation and utilization. Each of us participate actively and help the others. As a conclusion, the goal of this research was to replace quantitative and modeling and analysis with visual manipulations of the system behavior. As shown by the end of our outcome, we were successful in using our balanced mathematical model and meeting our design goals. It is important to note that there are several potential solutions to our problem and that the design of our PID controller would call for the usage of an active circuit. So that's all from our group. Thank you.